Well, hello and welcome to this webinar. My name is Esther Sumner and I'm a lecturer in geology here at the University of Southampton. So our aim with this webinar is to tell you all about what is geoscience, how can geoscience help save our planet, and how can you play a part in that? So what are we going to cover in this webinar? Well, the webinar will take about an hour in total, and I'll kick off with a presentation all about what is geoscience and how all the sciences used to study the Earth system. And then I'll hand over to three of my colleagues who will give short talks addressing environmental challenges and some of the UN Sustainable Development Goals. So Tim Henstock will talk about sustainable energy solutions. Then Gavin will talk about climate change, past and future. And then Lisa McNeil will talk about resilience to geohazards. And hopefully by the end of all that, you'll be really inspired as to what geoscience is. And my colleague Jessica Whiteside will talk about careers in geoscience and how you can become skilled for the future jobs market. And then for our final presentation, we'll have a short video by one of our alumni, Sean. So Sean did the 4-year undergraduate degree here in Southampton. He actually did that degree in geology, and he'll talk about his experiences studying in Southampton, in his lectures, the labs, in the field, and during his undergraduate research project. And then at the end of the webinar, we'll have a question and answer session. So what I suggest is, if questions come up for you during our presentations, then if you could write those questions down in the chat, then we'll answer those at the end of the webinar. But also, if you think that somebody else's question is really interesting, then hit like so that we can see that people are particularly interested in the answer to that question. And what we'll try to do is go through our answers sort of in the order of popularity of questions. So I guess I'll kick off with my talk, which is all about what is geoscience and how are all the sciences used to study the Earth system. Now, I would imagine that right now you're studying some of the following subjects at school or at college, so geography, physics, biology, maths, geology or chemistry. And I'd also imagine that you're wondering what you want to do with your future. Now, the fact that you've chosen to come to this webinar suggests that you have an interest in the Earth, or maybe you're worried about the future of the Earth. Well, geoscience is the study of the whole Earth systems. And by that, we mean the land masses, the oceans, the atmosphere, and the interior of our planet. And then as geoscientists, we study the Earth in the past, but also in the present and looking to the future. And as geoscientists, we also study other planets within our solar system. And we use all of these subjects that you may currently be studying to sort of understand the Earth. Now, many people have a misconception about what geoscience is, so I thought I'd tackle that misconception head on. So the misconception is that geoscience is all about oil and gas and mining and exploiting our planet's resources. Well, this is wrong. So geoscience is the solution to current and future challenges faced by us and by our planet. And this is what we like to focus on here in Southampton. How can we use geoscience to actually solve some of our planet's problems? Now, we can't really get away from the fact that we use lots and lots of energy. So right now I've got the lights on, so I'm using electricity. I'm using electricity to power this computer. This computer's made of all sorts of natural resources. So there's plastics, there's precious metals, there's rare earth elements in there. So we really do need to find sustainable ways to meet our energy needs. And geoscientists are involved in finding sustainable energy solutions, now whether that's wind power or tidal power or other things. And geoscientists are also involved in sort of solving some of the problems which we've created as people. So, for example, the increasing amounts of greenhouse gases like carbon dioxide in our atmosphere. And so I have colleagues who are working on, for example, ways in which we can capture carbon dioxide from industries before it gets into the atmosphere and starts causing problems. So, for example, they might capture the carbon dioxide and then store it in porous rocks deep beneath the Earth's surface. Or, for example, they may react that carbon dioxide with oxides in order to form more inert substances like carbonates, for example. And so my colleague Tim Henstock will talk to you more about sustainable energy solutions and also carbon capture and storage. So the geological record actually encapsulates the history of life on Earth. And so I guess we go from the weird and wonderful creatures of the Precambrian through to the dinosaurs, through to people. And the geological record also encapsulates a history of the things that have affected life on Earth. So this could be, for example, catastrophic events like meteorites impacting the Earth, or it could be periods of intense volcanism. It could be changes in sort of the plate tectonic setup, so the distribution of land masses and oceans on the planet, or it could, for example, be changes in our climate through time. And my colleague Gavin Foster will talk to you about his research group's work into climate change, both in the past and then also looking to the future. And then, of course, as geoscientists, we also study geohazards. And so, in particular, actually, as geoscientists, I guess we're interested in how do you protect human populations from these hazards. And so the types of hazards we study, so there's obvious things like volcanoes. So here we've got a volcano with a lava flow. So this is quite apt given what's happening on La Palma at the moment. But I guess we have other types of volcanoes which can be more explosive. So, for example, they might produce these avalanches, fast-moving avalanches of hot rocks and gas that are really destructive to anything in their pathway. I guess closer to home, as geoscientists, we also study things like flooding. So why, when, where does flooding occur? And actually, how do we protect people and businesses from that flooding? Then, as geoscientists, we also study really catastrophic hazards. And so this could be things like major earthquakes and consequent tsunami. And so my colleague Lisa McNeil will talk to you more about geohazards. So hopefully I've just given you a real whistle-top tour of a few areas of geoscience, so a flavour of the types of things that we study. And at the start of the talk, I mentioned that actually as geoscientists, we use all different science subjects to sort of answer specific questions. So to give you an idea of that, let's say you're studying, say, maths or physics at the moment, one of the ways we might use physics in geoscience is to actually image what the interior of our planet looks like. So, for example, we can image tectonic plates as they're being subducted, and we can use that to better understand actually how are the world's biggest earthquakes generated. Geology and geography also really important. So in geography, you might well be learning about modern environments on the Earth's surface and modern processes. Well, we can use what we know about modern environments in order to interpret the environments that we find in the geological record. And what's really, really neat if we can interpret environments in the geological record is we can actually look at how environments change through time. So, for example, an area might have gone from being a lake to being a desert. And so we can actually start to ask, well, why did that occur? And what might happen in the future? Biology is obviously really, really important if you're interested in studying the history of life on Earth. And so that could be, large scale animals, so things like mammals and dinosaurs, or it could be the microfossils of single-celled organisms that we find in the oceans. Chemistry is really important. So, for example, if we take those microfossils, we can use chemistry to measure the ratios of oxygen isotopes within those microfossils, and we can use that to actually understand what the temperature on Earth was like when that microfossil was alive. Or similarly, we can pick up a rock from the surface of a volcano, we can analyze the chemistry of that rock, and we can actually understand the chemistry of the magma chamber underneath that volcano and better understand what types of eruptions might occur. So we don't expect you to have studied all of these subjects at A-level or what have you, but this is just an idea of actually how we use lots of different subjects in geoscience. And actually, if you do a degree in geoscience, you get a fundamental grounding in lots of different areas of science. So if geoscience is something that you're interested in, then my colleague Jessica will talk more about careers in geoscience later on in the webinar. Now, if you are interested in a career in geoscience, then obviously you need a degree in geoscience. And here I'm just highlighting the degrees that we offer here at the University of Southampton, and to give you an idea of what they mean. So geology is the study of the whole Earth system. Geophysical sciences and geophysics basically mean the same thing. And so with geophysics, we're using physics to study the Earth system. Whereas with environmental geoscience, well, environmental geoscientists are looking at the sort of human interactions with the Earth system. And then the photograph behind me is quite appropriate today. So in a geoscience degree, you tend to do quite a bit of field work. And actually here are some of our students studying the volcano on Tenerife. And so this is part of a third-year module into volcanic and magmatic processes. And actually our students are there as we speak, actually studying this volcano. And then in terms of why study with us here at Southampton, Well, we're based in the National Oceanography Centre, which you can actually see in the background to this slide. So that sort of thing that looks like a greenhouse is actually our canteen. And so the National Oceanography Centre in Southampton is one of the world's largest centres devoted to research, teaching and technology in earth and marine science. Earth science at Southampton's ranked 7th in the UK for academic rankings of world universities. We're ranked in the global top 50 universities for geology. And it's really important to us that if you study here, you'll develop the core skills highly requested by employers on both marine and terrestrial field trips and residential courses. And so in fact, this small research vessel here is sort of a research vessel which we use for teaching some of those marine trips. And so I guess you don't have to take this from me. So towards the end of the webinar, we'll have a short video by one of our alumni, Sean, who can give you his opinions of studying in Southampton. So I guess I've probably talked for long enough. I'll stop talking. And what we'll do now is we'll move on to these 3 short talks by my colleagues addressing specific environmental challenges. And I'll begin by handing you over to Tim Henstock, who'll talk about sustainable energy solutions. So thank you.
Hi everyone, as Esther said, I'm Tim Henstock. I'm a professor of geophysics here at the University of Southampton, and I'm going to talk to you a bit about sustainable energy solutions and really how is it that geoscience is being used and how we can train you as geoscientists who will be able to address these key problems that we now have as we look forward as a society. I mean, you're probably really well aware by this point of the climate emergency problem and the agreement that was reached in Paris 2015. It turns out that agreement requires 2 things. First off, we have to reduce real CO2 emissions. So we have to move towards energy production, which is coming from renewable techniques. And we also are going to have to transition during the next few decades to actively removing CO2 from the atmosphere. We can't just leave all of the CO2 that we have put into the atmosphere there, because we won't be able to meet the objective of limiting the temperature increase. So if we're interested in renewable energy, how is it that geophysics and geoscience generally is involved in this? I've got an example on the left-hand side of the screen here. So this is a data set where we do an exercise in one of our modules where students are basically trying to evaluate an area as a potential site for a wind farm. And to be able to do that, we have to build what's called a ground model, and that includes the seabed. So the seabed on this image is the 3D colored surface here, and then we also have to investigate what's underneath the seabed. What's underneath the seabed is basically where our foundations are going if we want to put up a set of wind turbines. So understanding the nature of those sediments in the top few tens of meters underneath the seabed is really critical, and that's something that really we can only do with geophysics. Once we've got our wind farm in place and operating, this slide down at the bottom here is a survey that we were doing around a large wind farm in the North Sea a couple of years ago, and we're actually carrying out a geophysical investigation to monitor what effect the wind farm is having on the environment and how the environment is affecting the future success of that wind farm. Now, if we're generating energy offshore, we also need to be able to get that energy from where it's being generated to the land. And increasingly, when we may be generating energy off the north of Scotland, for example, but there's no wind off the south of England. So we have to be able to transfer energy from one area where it's being generated to other areas where it's being used. And mostly, certainly in the UK, this is done with high voltage power cables that are put on the seabed. So the map here shows a range of different existing power cables that are in red and some planned power cables in blue. And then the different colors on the map show different types of sediment on the seabed. So why is it important to understand the type of seabed sediment that's on the seabed? Well, it comes down to the nature of the cable. So this is a picture of a cable. We've got a conductor in the middle, we've got conductors around the edge, and then in between there is an insulator. And this insulating material is something which is fine up to temperatures of about 90 Celsius. But if you heat it more than that, then it will start to break down and the cable will fail. And so understanding how the heat is transferred away from the cable is really important. On the right hand side of the picture here, we've got a couple of models where we've basically taken the fundamental physics principles of energy transfer. So we've got sediment which has got water in it, which is potentially able to move around between the sediment grains. We've got conduction of heat energy going on, and the difference between these two models is a sediment property called permeability. The lower model here with the big red arrows are showing that there is hot fluid which is moving around within the subsurface there, so we could generate convection around the cable in the case where the permeability is high, and we only have heat transfer by conduction if the permeability is low. So the high permeability sediment is really nice if you're a cable engineer because it keeps your cable cool. So understanding that environment is critical. Now, if we want to do something about the CO2 in the atmosphere, then we need to move towards carbon capture and storage. And there are two ways that we can do this. So one is to capture the CO2 and potentially store it in subseabed reservoirs. And so we've been investigating how gas is transported, how gas moves around beneath the seabed. So this is, on the left here, is a cross section which is extending up to about 50 meters underneath the seabed in a part of the North Sea called Scanner Pockmark, this big hole in the seabed here, where gas has naturally been escaping from the system over the past certainly a few hundred and probably a few thousand years. So these bright reflections down here that we can image using a method called seismic reflection profile. These bright reflections correspond to concentrations of gas that are moving around and then coming up to the seabed. And on the right hand side here, you can actually see this is an image of gas escaping into the water column. So we can estimate how much gas is escaping from this system as a function of time, and use it as an analog to understand what might happen if we start to store carbon dioxide in similar formations. Alternatively, we can get rid of carbon dioxide basically by turning it into stone. It turns out that if we take basalts and mantle peridgotites, so these are rocks that are fairly common within the earth, and we react them with CO2, then we end up forming carbonate minerals such as calcite and magnesite. The key advantage is that these minerals can't escape. They are basically locking up the CO2 for very long periods of time. And one of the sites that one of our colleagues is involved in working is this Carbfix test site in Iceland, which is an industrial scale experiment at this kind of process. So it's a geothermal power plant. The geothermal power actually produces CO2 coming up from depth. The CO2 is dissolved in water. That water is then pumped down into a location where it can react with the basalts. And on the left-hand side here is an example of a really exotic technique, which is a micropositron emission tomography experiment, showing a sample of basalt from this reservoir, and then over time this basalt has had fluid injected into it, and the question is, how does the fluid move through this potential reservoir rock, and how does it therefore react? So using some really exotic physics, really exotic chemistry to be able to solve this key societal problem. Now I'm going to hand over to my colleague Gavin, and Gavin is going to talk to you about past and future climate change.
Oh, I'm on mute, aren't I? Terrible. What a mistake. Right. Can everybody hear me? I hope now. Right, I'll start again. So yes, my name's Gavin Foster, and I'm professor here at the University of Southampton. I clearly don't know how to use Teams, but I am going to talk to you about how geoscience can give us insights into past climate change and how we can use that to inform our predictions of the future. Now, we've heard already this webinar about climate change that's happened over the last 150 years, where we've seen global temperatures increase by about 1.2 degrees C. This has caused increased extreme weather events. It's caused heat waves to occur more frequently. It's led to more droughts, and it's raised sea levels. That sea levels have raised both because the oceans have expanded because they've warmed up, and because the continental ice sheets have melted, and that melt has run off into the ocean. Now, one of the perhaps the best ways in which we can, or the best illustrations of this dramatic climate change is with the cryosphere. And if we look at this picture from the Engenbreen Glacier in Norway in 1889, so the beginning of that multicolored time series I showed you, it shows this nice Victorian gentleman sitting admiring the view of the glacier. And here's the same picture, same location in 2010. And you can see that the glacier's retreated up the mountain valley, and it's been replaced with this lush forest. Now, the reason this climate change is happening is because of atmospheric CO2 concentrations gone up. And of course, atmospheric CO2 concentration's gone up because we've been burning fossil fuel, we've been making cement, and we've been cutting down forests. I think that's pretty well understood by most people, and as it's being discussed in Glasgow, hopefully we're going to do something about this problem. Anybody who knows anything about geoscience knows the climate's always changed, right? So, and it's a common climate change denier point is, climate's always changed, so what? Well, what I want to tell you is that actually we can use that climate change to better the past climate change to better understand future climate change. Good illustration of past climate change is this is a picture of Antarctica today, penguins and ice. If we look at the rocks that stick out of that ice sheet, you can see ferns like this from a temperate rainforest that covered Antarctica in the Cretaceous. So there's so many fossils that we can reconstruct the past environment on Antarctica in the Cretaceous 120 million years ago, and it looked something like this. The Cretaceous was on the pole still. It's still on the South Pole, but the background climate was just so warm there was no ice sheet. What my research group does is use records of past climate change to try and understand the relationship between CO2 and climate, and trying to understand what that can tell us about the future. Now, we don't use fossil leaves, but we do use fossils recovered from the seabed using ocean drilling. Here's a sediment core that we recovered from the seabed. Here's a little microfossil that we recover from the sediment core. And then we take these to the geochemistry labs. Geochemistry labs in Southampton. Here's a rare picture of me in the lab. I don't get down there as often as I like to, but many of my students do, including my undergraduates. And here's a picture of me in front of a mass spectrometer measuring the minor chemical composition of these sorts of fossils and their isotopic composition. What we can do with this is we can reconstruct CO2 in the past, we can reconstruct climate in the past. And here's a summary figure that was in a report to the Geological Society of London about how the geological record can tell us about past and future climate. And what it shows is a bunch of different time intervals going back to about 55 million years ago. So the early Eocene, when temperatures were warm, CO2 was high. When temperatures were cold, like in the last glacial maximum 20,000 years ago, CO2 levels were low. So there's this nice correlation between temperature and CO2. Another thing that looking at climate of the past can tell us is we can put the rate of change that we see today in some sort of context. This is a summary figure from a paper that came out a couple of years ago by David Kemp and others. It shows time span of a particular geological event in the past and the rate of temperature change during that event. Don't worry too much about all these dots. The bright colours here, the oranges here are those events that are associated with big extinctions. So the Permo-Trias here is where 96% of all species became extinct. If we put a modern event on, it's off the scale. It doesn't even fit on the same scale as these geological events. It's very rapid, much more rapid than anything in the geological record. Certainly anything in the last 66 million years, because 66 million years ago we were hit by a meteorite that caused radical change, wiped out the dinosaurs, killed the ammonites, that sort of thing. So basically what we're doing, what the geological record tells us is we're doing something that is very fast indeed. And finally, the last thing that my research group uses the geological past to tell us about is how we can refine the predictions of our future climate. So we built a climate model with colleagues, integrated that climate model with observations of the past climate, and its predictions are shown here in this blue line. So this is with a high emission scenario, so we're chucking out lots of CO2, and our model predicts a narrower uncertainty of warming than the unconstrained sort of models that the IPCC uses. This is important because it narrows the predictions of how warm the climate will be, but importantly it gives us the timescales at which we have to make the change to hit these climate targets. So I'll just finish by showing you this quote from Charles Lyell, the famous Victorian geologist, that the present is the key to the past. It's the uniformitarian principle that underpins geology and geoscience. But actually, when it comes to climate science, I hope I've convinced you in this 5 minutes that the past really is the key to understanding our future. And with that, I will pass over to Lisa McNeil, who's going to talk to you about resilience and geohazards.
Thanks very much, Gavin. Okay, getting there. Okay, thanks very much. Hopefully we're not depressing you with lots of sort of gloom and doom, but we're also showing you that there are solutions and answers, and geoscience plays a big role in that, as Esther introduced at the beginning. So I'm going to talk a little bit about resilience to geohazards and focusing on volcanoes, earthquakes, tsunamis, and the coastal zone. So what can geoscientists do to increase our resilience, and what is resilience? So we have, as you know, many hazards within the natural world. So we need to first of all assess what that hazard is, and then we go on to assessing the risk to humans and infrastructure. And after that, we can then try and mitigate or decrease that risk. And as a result of that, we increase our resilience or ability to cope with those sorts of hazards. And the geosciences, including geology, geophysics, and environmental geoscience, is used primarily to identify and assess the hazard. So, for example, we find the active volcanoes, the places where the earthquakes will occur. We work out how big the hazard is, for example, from past events, and also by using monitoring in the present day. And we also image the surface and the subsurface to reconstruct the geology and the environment. And so from that, we can then forecast areas where the risk is greatest. And this is then used by engineers, including engineering geologists, to reduce that risk by mitigation and thus making communities more resilient. So I'm going to show you 4 examples of this. So first of all, talk about earthquakes and tsunamis, and particularly focusing on subduction zones. These are the areas where one tectonic plate goes beneath another and they converge together. And these are the areas where the largest earthquakes and tsunamis are generated. And these have been in the sort of news headlines in recent decades. And you might remember, particularly in 2011, the Japan earthquake and tsunami. And on the right, we've got an example of another subduction zone in Japan. And here we've got a combination of different geological and geophysical data sets, which are imaging the subduction zone and the fault, which is generating these large earthquakes where the plates move together. So as geologists and geophysicists, we can do a number of different things here. So we can collect those geophysical data to image the faults and their properties underneath the seafloor. We can also drill boreholes, and we can collect samples deep down within those fault zones, and we can work out what the actual physical and chemical and geological properties of the faults are, because that controls how the earthquake will occur, where the earthquake will occur. And we can take those samples back to our labs and do experiments with them. We can also use information about past records of earthquakes and tsunamis from the coastal geological record in this case. And we can also do some live monitoring. So the red lines that you can see here are all cables on the seafloor, which are connecting to instruments on the seafloor and underneath the seafloor. And these instruments are measuring movements, small earthquakes and changes in pressure and temperature and fluid flow. And these are feeding back information live to land. And so they can potentially give some kind of advanced warning of an earthquake as it happens, and giving some time before potentially a tsunami arrives on land. So this is one example. A second example is man-made earthquakes. So this is an example from Oklahoma in the US. And what's happening here is that wastewater is being injected underground, and as a result, it has generated earthquakes. And these earthquakes can be quite large. So you can see the magnitude here goes up to magnitude 6. So this is a cross section, and it's showing different volumes of fluid that have been injected into the ground, and then a cluster of earthquakes that have happened underground. So this was from a project that was done by colleagues here in Southampton. And what they were able to do was combine a number of different geological and geophysical approaches. So first of all, you want to know where the earthquakes are occurring. So we use geophysics to monitor and record those earthquakes. We also use geology and geophysics to investigate underneath the ground, to find out where the rocks are, what type of rocks they are, what are the properties of those rocks, and therefore how fluids might behave within them. And then what was special in this study was they then modelled how that fluid being injected was creating the earthquakes. And by doing that, they were able to make suggestions about volumes and depths of fluid injection that would reduce the earthquakes that were generated. So this is actually mitigating the hazard that's occurring in this area. This is going to become more and more important. It's a hot topic, and as we obviously need to carefully dispose of our waste and our pollutants, we need to do that so that they don't actually generate in additional hazards as well. A third example is volcanic hazards. So this is from the Ethiopian Rift Zone, which is in East Africa. And here, some different methods have been used to try and reconstruct the eruption history of the volcanoes here, and then to use that to forecast which volcanoes are most active, where lava flows from those volcanoes erupting will go, and therefore to try and work out where the hazard is greatest, and then take that into account when it comes to people and infrastructure. This again was a study from Southampton, and what they were using here was actually satellite data imaging the surface, where you can actually see differences in the different lava flows, which are a function of their age and composition. And on the right, you can see how those different lava flows were mapped out. In addition, some samples were taken, and those give information about how old the lava flows are, and also about their chemistry, which tells us something about how the flow might behave and how they might be related to each other. And so this is a really good example of a study where you can potentially remotely do a lot of analysis of an area. So this is particularly important for areas that are maybe difficult to access or potentially even unsafe. And then my final example is looking at the coastal zone, and particularly thinking about coastal erosion and flooding. So this is an area where geology and geophysics is combined with oceanographic studies to try and evaluate the nature of the rocks and sediments in the coastal zone, how likely they are to be eroded, and then how are they going to be impacted by waves and tides and future rising sea levels, and then to put that into some kind of management and mitigation plan so that we can understand how infrastructure and populations are going to be affected, and hopefully try and reduce that. So we've got a really nice image here. This is an area of the coast offshore Dorset. Some of you might recognise the Isle of Portland. And this is using bathymetry to image the seafloor, and we can actually see some of the rock layers and the sediments that are filling in the gaps between those rock layers. So some of the things that geologists and geophysicists and environmental geoscientists might be involved in here, they might be involved in those bathymetric surveys, and also maybe some surveying of the shallow undersea floor structure as well. They might also be using remote sensing so that they can image the morphology and the geology of the onshore part of this, and they might also be involved in looking at the topography of the beach and the cliff. And from this, they can hopefully analyse the nature of the rocks, their physical properties and their erodibility, and help to contribute to reducing the hazard here. And so I'll now hand over to my colleague Jessica, who's going to talk about careers. Sorry, I'll stop sharing. There we go.
Hello there, everyone. I'm Jessica Whiteside, and I'm an associate professor in ocean and earth science and the admissions tutor for geology, environmental geoscience, and geophysics. And I'm going to talk to you today about exciting careers in geosciences and how you can prepare yourself for your future job. Next slide, please. So the first thing I want to start with is that a degree in geoscience is a passport to a career in a wide variety of different pathways. Geoscientists are currently recognized by the government as being in very short supply. In fact, they're number 5 on the list in the UK shortage occupation list, but they're key to meet strategic needs within the UK for a sustainable future. And you can see this is the report from October 2021, and that physical scientists, including engineering geologists, hydrogeologists, geophysicists, geoscientists, geologists, geochemists, senior resource geologists, and staff mining geologists are in short supply, and their skills are greatly needed as we work towards our sustainable future. Next slide, please. So where will you find yourself? Well, these positions might find you in a university, a governmental organization, research council, a consultancy firm, an energy company, charities or aid organizations, or a vast array of other places. And I'm going to break these down into 6 geoscience career pathways. My colleagues have already hinted and alluded to some of the exciting careers that you could have within them. So we have natural hazards and risks, and Esther and Lisa talked to you about some of these natural hazards. As Lisa discussed, this is focused in on understanding, modeling, assessing, and possibly mitigating the impacts of geological and environmental hazards on the environment and livelihoods. You've heard about volcanoes, earthquakes, and tsunamis, and what we can do about the effects to human populations. And then moving next, sustainable energy and climate change. So here, focusing in on mitigating climate change, influencing governmental policy through understanding past climates, like what Gavin talked to you about, modeling potential future scenarios, and understanding the subsurface to harness geothermal energy, enable safe infrastructure development, and carbon capture and storage, so all solutions based on technologies as Tim shared with you. Environmental geosciences. So here, assessing the interactions between human activities and natural environment. Environmental geoscientists want to understand and monitor the drivers of environmental change, so climate change, and the risks of things like microplastics or emerging contaminants and how these affect local water bodies. Moving on to hydrogeology. Hydrogeologists are ensuring access to clean and sustainable water supplies. Then we have mining and quarrying. So here, sourcing and extracting critical minerals needed from green technologies, so things like solar and wind power, as well as nearly every single natural item that you touch. So the resources that we have around us, they're all sourced by geologists, whether it's concrete, iron, copper, gold, lithium batteries, rare earth elements. In fact, the computer screen or the phone that you're actually watching this webinar are all sourced by geologists. And finally, research, teaching, and outreach. So we have curators of the fossil record, people working in museums. These are geologists, paleontologists. There's also outreach in the terms of professors at universities and school teachers. Next slide, please. So we're just going to take these one by one, and you can see a series of potential positions that your future career might be, and then the types of companies or agencies that might be hiring you. So natural hazards and risks Could be a volcanologist, a seismologist, an engineering geologist, a hazard consultant, an erosion specialist, all focused in on these natural hazards and risks and mitigation and assessing and monitoring the situations. Next slide, please. We have sustainable energy and climate change. Could be an exploration geoscientist, a geophysicist monitoring that subsurface and ways of storing carbon management and sequestration. You could advise policymakers or be one yourself, and city developers, all focused in on sustainability. Next slide, please. For environmental geoscientists, also greatly in demand, you could be a geoengineer, carbon management as well, a civil engineer, an environmental planner or consultant, a conservation manager, or an environmental geochemist monitoring changes to the Earth's surface and water bodies. Next slide, please. Hydrogeologists, these include geotechnical engineers, hydrogeologists, civil engineers, groundwater modeling, all focused in on clean and renewable water resources. Next slide, please. Mining and quarrying, we have exploration geoscientists, other companies that include blue mining, so focused in on breakthrough solutions for sustainable deep sea mining. There are oil and gas producers, exploration companies that are sometimes incorporated into the producers, as well as consultancy agencies. Next slide, please. And research, teaching, and outreach. There are museum curators, university professors, school teachers, research geoscientists for a variety of agencies, and then in unique fields like forensic scientists, where you can help assess things that deal with actually policing and other entities like that. Next slide, please. So as you can see, the geoscience career pathways are quite diverse. This picture has an awful lot of arrows, a lot of things going on, just to underscore that the various fields are all interrelated, they're very connected, and one of the beautiful things about geoscience is that anything you know about anything at all comes into play. So you can see how interrelated the fields are. Now, how can you actually situate yourself for a career in geoscience? Well, that's to start off with a bachelor's degree. Here at the University of Southampton, we have tailored modules that fit you as you're seeing yourself growing as a geoscientist. You want to situate yourself so that you have access to relevant work and field experience and take opportunities of career days and the techniques and the skills that former alumni who come back onto campus and give short talks and have meetings with students. You want to take an opportunity to capitalize on those events. Join organizations like the Geological Society of London has a student organization, and possibly do postgraduate work. What you want to be doing, though, is playing to your strengths. So particular modules that suit you best, hang out with other geoscientists, and most importantly, have fun. Next slide, please. So at the University of Southampton, we keep track of where our alumni go and the jobs that they have. And as you can see on this pie chart, this is a compilation of data where we've gathered where our geoscience graduate employment destinations make. And you can see that over 90% of our geoscience students are employed or went on to further study within 6 months of their graduation. And I want to point out that this is actually a minimum estimate because an unknown destination of a student does not mean that they're unemployed. So we have 90% going on for employment, and among those students who secured employment or went on to further study, almost 60% of them, that's in this orange part of the pie chart here, were employed in a range of careers in environmental monitoring and management, geotechnical engineering and environmental hazards, in mining, natural resources, these sectors. Another 22% went on to do a PhD or master's degree. And because of the transferable skills gained with a geoscience degree, 21% of them secured jobs in management, finance, or software technology companies, and many of these are related to geoscience as well. Thank you.
Oh, okay, sorry about that. So we've now reached the final presentation in our webinar. So you're going to hear from one of our alumni, Sean Hemming. So unfortunately, Sean can't be with us this afternoon. He's busy, I think, doing field work. So we've got a video from him instead. And so in this video, he's going to talk about his experiences studying in Southampton. So Sean actually studied the undergraduate integrated master's degree in geology. So that's the 4-year MSci in geology. And he'll talk to you about his experiences doing his undergraduate research project and on field work and all sorts of things. So I'll let him talk for himself.
My favourite part of the degree was probably the 4th-year master's project, because I had the opportunity to conduct some original research and make a mark on the forefront of modern science. Hi, I'm Sean. I'm a second-year PhD student at the University of Southampton. I recently graduated here with a Master's in Geology, and I'm going to be talking to you about some of the things I got to do as an undergraduate, some of the skills I gained, and how it led me to where I am today. Geology is a broad subject with a number of different areas, meaning that it can be appealing to people with a range of different interests. So for example, if you enjoy biology, then there's paleontology. If you like physics, then there's plate tectonics or seismic activity. And if you prefer chemistry, then there's things like mineral exploration or magma composition analysis. Because geology, geophysics and environmental geoscience are such broad topics, research facilities need to have a variety of specialist equipment to be able to cover these areas. The National Oceanography Centre Southampton, or NOGS, is home to a wide range of equipment and staff that perform cutting-edge research on a daily basis. This means that lecturing staff are world leaders in their fields and can include the most up-to-date information in their teaching. In addition to regular practical sessions, I had the opportunity to go on a number of field trips and practice my mapping skills, including Spain, Ireland and Tenerife. Because each trip visited a different location, I got to see a variety of geological settings and features, which was really interesting to see and helped to reinforce what I'd learnt in lectures. For me, the Spain trip was my favourite because of the number of rare things that we got to see. So, for example, we got to see a vein of gold ore from a disused mine, and on a different day we got to see a garnet volcano. So it was a volcano that when it did erupt, it would bring magma to the surface along with these little purple semi-precious gemstones known as garnets. My favourite part of the degree was probably the 4th-year master's project, because I had the opportunity to conduct some original research and make a mark on the forefront of modern science. My project investigated the removal of technetium from groundwaters at nuclear sites. So when a nuclear power plant reaches the end of its lifetime, all the contamination must be cleaned up and removed, and technetium can be a common contaminant in the groundwater. So my project focused on whether we could use a powdered chemical framework to remove the element from water. This work was really important because nuclear contaminants can cause a lot of harm to the environment, both the local populations and the wider environment. So we must deal with any problems to protect both of these things for the future. At the start of my project, I spent a few days in the chemistry department up at Highfield campus. After, I performed experiments down at Knox and was able to use the facilities to aid me. Being able to use all the facilities that the university had to offer made me realise just how much I enjoyed lab work, leading me on to where I am today. I'm currently working on using electricity to remove radioactive contaminants from materials found at nuclear sites, so the skills I gained throughout my degree have been invaluable to me and have allowed me to excel in my current work.
Okay, well, that brings us to the end of all of our presentations. I hope that you really enjoyed them and that you're quite interested in geoscience. And so if you have any questions for us, if you could put those in the chat, that would be brilliant. And I'll hand over to my colleague Lisa, who will chair the question and answer session. Thank you very much.
Thanks very much, Esther. And thanks everyone. Okay, so we've had quite a few questions in the question and answer area. I'm going to hand over to my colleague Jessica, who's going to answer the first one that we had, which is actually about A-level grades and subjects. So hopefully Jessica can help to answer that, and that was quite a popular question.
So that's a great question, and we have 3 different degrees at the bachelor's level within the broader geosciences. We have a bachelor's degree in geology, a bachelor's degree in environmental geoscience, and a bachelor's degree in geophysical sciences. Now, the requirements for geology and environmental geoscience are the same, where the A-level grades are A, B, B, including a preferred science subject. Those preferred science subjects, as you saw, the sciences are interrelated in geology, and it depends on which area you want to go into. But these sciences include biology or maths or chemistry, geography, environmental studies, physics, geology itself, computer science or electronics. And in terms of geophysical sciences, the A-level grades are A, B, B, including physics and math. And hopefully that answers your question.
Thanks very much, Jessica. Sorry to put you on the spot there. I do actually have the list of the preferred science subjects, so maybe I can post that into the Q&A as well, if that helps. Okay, so let's have a look at the other questions that we've got. So that was the first one we had. Another one that's I'm going to have a go at answering a couple. So quite a lot that are quite popular. There was one question that cropped up, which is Earth science the same as geoscience? That's a really interesting question. I mean, in some ways they are really sort of synonymous and the same thing, but Earth science places sort of more emphasis on the planet of the Earth, and it also encompasses more the oceanographic part of the Earth. So as we know, the vast majority of the surface of the Earth is covered by the oceans. So I think it has a sort of a bit of an element of thinking more about those different systems and how they interact. So not only the Earth system, but also the ocean system. So that would be my take on those definitions. But that's a good question. And you probably will see them interchangeably if you're looking at degrees and the subject. Okay, let's see what else we have. So we've got a question here, and I might send this one, if you don't mind, back to Jessica. I'll put you on the spot here. This is the one about what skills would you say make a successful geoscientist? And we could all sort of pitch in with that, but the difficult one.
I think the skill set is a willingness to explore really the Earth and all its dimensions, from the subsurface to the surface layers to the atmosphere, and then actually as the Earth is one planet itself and the broader implications of planetary geologists. So I think number one is really an ability to explore, an ability to see things from multi-dimensions. So to be able to see something from the outcrop and think a little bit about what that means in terms of the chemical components of the rocks that you see and the depositional environments of how they actually were laid down. I don't know if anyone else wants to chip in on. Tim, I think, has volunteered to also talk a little bit about skill sets.
Yeah, so I mean, as a geophysicist, in my day-to-day work, I am using skills from physics, I'm using skills from computing, I'm using skills from maths, and drawing those together with things that I've seen when I've been out in the field to be able to try and kind of understand, well, okay, does what I'm trying to do with the physics and maths actually make sense when we look at real rocks and how real rocks behave? So there's, I think the key thing is that there are lots of different ways that you can specialize within the geosciences, and so you kind of bring the skills that you've already got, and you bring the interest that you've already got, and you're able to apply those in a whole range of different directions.
Thanks very much, Tim. Sorry, there was a delay on me unmuting my mic. Hopefully that helped and gave you a couple of different perspectives on the skills of geoscientists from Jessica and Tim. There's quite a few other questions, so I'm just going to work my way through them. In fact, I'm going to answer one of them, and then I'm going to about how many years of study, and then I'm going to hand over to Esther to give her perspective, if she can see the questions on the traveling around different parts of the world. So I'm trying to line up the Q&A, which is not coming up. Okay, hopefully you can still hear me. I can't see the Q&A, but I think I can remember the question. So there was one question about how many years of study. So the degree programs that Jessica showed, and Esther and Jessica have sort of described, we have 3 and 4 year degree programs in Southampton, and that's fairly typical in most of the universities around the UK. So the 3-year degree gets you a BSc, and the 4-year degree gets you a what we call an MSci, which is an undergraduate integrated master's. Bit of a mouthful, that. So some people do go on to further study. So some people might go on to do a master's of 1 year, some people might do a PhD, but a lot of our students will go directly from those 3 or 4 year programs into a job. Esther, are you able to make some comments about going to other places in the world?
Sure. Okay, so I guess most of our undergraduate degrees include some foreign fieldwork. So all of our courses include residential field trips. So, for example, as a geologist or environmental geoscientist, that might involve in your second year having a 2-week field trip in southeast Spain, which is a fantastic trip where we teach all sorts of different areas of geoscience. Also, as I kind of said in my talk, some of the modules involve foreign fieldwork. So, for example, a volcanic and magmatic processes module. We've got students in Tenerife doing fieldwork at the moment. Where else am I missing? So for your independent mapping project, then obviously that's a little bit different at the moment with COVID, but that in the past has involved students choosing to go to all sorts of different locations, depending on actually what particular area of geoscience you're interested in to go and do your project. And then the geophysicists have some field work in Brittany, in France, to learn specifically about the physical techniques that you can use to measure the Earth. So there's a whole host of different foreign field trips that you would do as an undergraduate student. I don't know if anyone else wants to comment on all the ones I've probably missed.
I was going to add just a little to that, but sometimes it is possible that undergraduate students can take part in research trips and even research expeditions on ships that we go on. It's more common for people to do that when we have master's students and PhD students, but it certainly can be possible. So I was just going to add that in. Okay, Natalia. Okay, I think we have some technical problem apparently. I think you're seeing a presentation playing. We will try and resolve that. I hope you can still hear us. If you can still hear us, then we can hopefully relay the questions to you and give you the answers. And apologies that there's a presentation playing in the background. Okay. Okay, we'll carry on. We have a colleague who's with you in the audience, so she can hopefully relay what's going on to us, and we'll carry on. Okay, so I've got a few more questions. There's quite a lot of them. Some of us will try type in some answers because we won't be able to cover absolutely everything verbally. So let's have a look and see if there's anything else that we have. So I'm just going to give a couple of quick answer questions, then hand over to some of my other colleagues. So how do these degrees compare to a degree in geography? I think I would argue that this might sound a bit biased, but we go further than a geography degree in terms of the physical geography aspects, because not only are we looking at the surface of the Earth and the modern processes, but as our colleagues described, we're also looking at the subsurface and all the way down to the core of the Earth, and looking way back in time in terms of the history of the Earth and changing environments. So we do that rather than focusing only on the surface and modern processes, which tend to be more what you would cover in physical geography. So we do what you see in geography and much more. So I think that's how we would describe the difference. But we are a bit biased. How much oceanography does geoscience involve? Well, one of the things that's actually very positive about coming to Southampton, the Oceanography Centre, is we're based in an oceanography centre and we have a School of Ocean Earth Science. So you have the opportunity to take modules that are much more oceanographic. We have several modules that cover the whole span of the Earth and ocean system, and then we have some specialised oceanographic modules that you can take as well. So that's relatively unusual. But it's important because, as many of us have described, there's quite a lot of links between these different systems. So it's important to understand that rather than just stopping at the sort of surface of the Earth and not how it interacts with the ocean, the atmosphere and ecosystems. Okay, Gavin, not much warning here, but I'm going to ask you if you can answer the question which says, what degree in geosciences would relate more to the future modern world, or maybe sort of comment, you know, what you feel sort of best equips people for some of the aspects you discussed. Okay,
can you all hear me? Yeah, I think that's the beauty of a geology degree. Is that you can turn your hand to almost anything. I mean, I during my degree I specialised very much in the solid earth and did a PhD on how mountains form. But those same skill set are what I apply to look at the geochemistry of microfossils to tell about the future. So, you know, there's no it's not you're not locked in with geology because it's quite a broad subject. But I mean, I would have thought the environmental geoscience degree and geology probably prepares you most for looking at understanding how our past climate can tell us about the future. But as Tim showed, you know, geophysics has a strong role to play as well in looking at finding the solutions for our climate problem. So, you know, I mean, I think geosciences are very broad. And I don't think any one of them locks you in a particular direction in your future, but all of them are very useful to understand and solve the future problems that the world faces.
Thanks, Gavin, and thanks, Tim, for your response there as well. Good answers. And Tim has also posted an answer about the work experience question, which one of you raised. So if you have a read of that, but basically he's saying it's fantastic if you can get it, but it's not necessary. And we do understand it's often difficult to get, particularly before you come to university. And we have opportunities, and many students can get some work experience during their degree. So there's a couple of questions related to geoscience degrees relative to natural sciences and geoscience versus geology. Jessica, I don't know if you can kind of answer anything on the sort of nuance of the geoscience versus geology.
Sure. So for the geology and environmental geoscience distinction, I mean, as we talked about, geoscience itself is such an overlapping field that all types of different fundamental fields come into play. But the way that we see it, environmental geoscience is really concerned with the interaction of humans and the natural world, so environmental processes related to that. The geology takes it a little bit further and considers the 4.5 billion year history of the Earth and the evolving coevolution of life and climate, the buildup of diversity and the breakdown in terms of mass extinction. So it's a little more encompassing in terms of the entire totality of the Earth and how we got to where we are now, whereas the environmental geosciences is more related to the interaction with humans and mitigation, not to say that they can't be in both, but more involved with risk assessment and mitigation of the human impact on the natural world. Thank you. Okay, we're getting very close to our time, so we probably should wrap up. I think we have actually one remaining question, and I think what would be maybe useful for you if you have other questions is if one of us puts an email into the Q&A so that you can post any additional questions that you might have. I don't know, Jessica, if it might be appropriate for yourself as the admissions officer, but that would probably be a good idea to do. But the one last question very quickly that I see is how does a geoscience degree compare to a degree in natural sciences? And just a very quick answer to that would really be the natural sciences degree would be broader. I mean, geosciences encompasses all of the sciences, but with a focus on the sort of the Earth system. Whereas natural sciences is obviously even broader. And some natural science degrees you can then specialise, but you probably wouldn't be sort of doing the geology aspect obviously from the beginning. We do have natural science degrees in Southampton if that's something that interests you, and it's certainly worth having a look at those and maybe coming to an open day and looking at the differences. Okay,
So I think if one of us can just sort of post an email, that would be fantastic, so that people can provide any additional questions to us. But I just want to say thank you to all of you for joining us. We hope you've learned something about Earth science, geoscience, and all of the other names for the subject that we study, and got an idea of what you could do with such a degree in your future life and help to hopefully save the planet and play a part. Okay, thank you very much, everybody.